Hello! In this lesson we're going to be learning more about alpha, beta and gamma radiation. Now as usual, make sure your phones are off, no TV on the background or games that you're playing, and you've got your booklet with you, and you'll need a periodic table as well. You might want to have one open online that shows all of it, not just the basic ones in the back of your booklet. So first off, we're going to have a bit of practice on these decay equations. We've got two lots to do. We've got ones that decay by alpha emission and then ones that decay by beta emission. You'll remember that the ones that decay by alpha emission, they will emit an alpha particle, which is a helium nucleus or has 2 protons and 2 neutrons, giving it a mass number of 4. We write the symbol alpha there. So the atomic number goes down by 2, and the mass number goes down by 4. For the beta particles, they will emit an electron. We write that as -1 charge, or then change the number of protons. We can write the beta sign and 0 mass. In this case, the atomic number increases by 1 and the mass number has no change, it stays the same. This is because a neutron is turning into a proton, so the mass number stays the same, but the proton number changes. When we change the proton number, we change the element. Now do pause the video and have a go at doing them. If you're still a bit unsure about how to do them, watch me doing the first few. You can then pause and check your answers. You should now only be watching if you're not sure what to do, or if you've already completed them all and want to check your answers. So my first one, I've got polonium-210, it has an atomic number of 84. I'm emitting an alpha particle, so my atomic number will go down to 82, it's going down by 2, and my mass number will go down by 4, which is 206. I look on my periodic table and I find the element that has an atomic number of 82, and that is lead, which has my symbol Pb. I also emit an alpha particle, which I have my 2 and my 4 there. If you've been watching because you didn't understand, do have a go at the next one now. Going through the next one, we've got 92, so uranium-238 has an atomic number of 92. That goes down to 90, and we get uranium, it's not uranium, sorry. It's no longer uranium. My mass number goes down to 2, 3, 4. I look at my periodic table and find what has an atomic number of 90, and that is thorium. I also have my alpha particle here. So I've got thorium, which is 90, and that will go down to 88. My atomic number going down by 2, and my mass number is going down by 4, and that will also be 2, 3, 4. I find on my periodic table what has an atomic number of 88, and that is radium. Again, I have my alpha particle. My last one, I've got radon, which is 86. That goes down, my atomic number goes down by 2, so I get 84. And my mass number goes down by 4 as well, and that gives me 218. I look on the periodic table and find what has an atomic number of 84, and that is polonium. I also have my alpha particle. So those are the first 4 done. We're now going to move on to our beta emission. So we're emitting an electron. So I know for all of these 4 down here, I'm going to have my electron being emitted. This part, I'm going to increase the number of protons, so my atomic number will increase by 1. This first one, I'm going to increase it by 1, So 6 goes up to 7. My mass number stays the same. I look on the periodic table and I find that I have nitrogen as an atomic number of 7, plus my beta particle. My next one, I've got strontium, an atomic number of 38, increases by 1 to 39. My mass number stays the same, and I have the atom yttrium. Plus I have my beta particle as well. I now have potassium. My 19 protons become 20 protons, and I get calcium when I look on the periodic table. My mass number stays the same. I still have my beta particle. My last one, I've got 7 protons, that will increase to 8, and my mass number will stay the same, still going to be 13. I then look on my periodic table and find out what has an atomic number of 8, and that is oxygen. I also need to make sure I include my beta particle. Well done if you've got those all correct. If not, do have a look at where I've done it or how I've done it, and see if you can see what I've done with just changing the number of protons and maybe the mass number if it's alpha emission, no change in the mass number if it's beta. So we're now going to have a look at the penetration and ionization of each particle. So radioactive sources are ionizing. That means they will crash into other atoms and knock off the electrons. Of other atoms. So they've made them into ions. If something's been ionized, we can say it's been irradiated, and it can cause damage. Now, alpha particles are the most ionizing. These are the most dangerous. They will knock off anything they come into contact with straight away. Beta particles in the middle, they're a little bit ionizing. Gamma rays are the least ionizing. They will pass through a lot of things before ionizing them. If we look at the penetration, so the distance they can go, alpha particles can travel about 2 centimeters in air before they stop, because they're ionizing any air particles they come into contact with. They can be quite easily stopped by a thin sheet of paper or your skin. Beta particles can travel through paper and skin fairly easily, but will be stopped by a thin sheet of aluminium. Their total distance in air is about 2 meters in air they can travel. Gamma, or X-rays, which are a type of gamma rays, travel at the speed of light. They will go until they are stopped by thick lead or thick concrete. So they will travel in air indefinitely. Or not indefinitely, but a very, very long way. In a vacuum, they'll travel indefinitely. So they are stopped by lead or concrete. And they all have different uses and different dangers. We're going to have a look now at them in a bit more detail for each one. We'll start off with alpha particles. So alpha particles, we'll remember, are a helium nucleus. They have 2 protons and 2 neutrons. And we can write it like this. This is my number of protons. This is my protons and neutrons, my mass of it. It's an alpha particle. And it has a 2+ charge, because there are no electrons to neutralize it, or to cancel out the positive charge. It's the most ionizing. So it will ionize anything it comes into contact with. And it only travels a short distance in air, again about 2 centimeters. And they are very, very dangerous. If they come into contact with your skin, they can cause the DNA in your cells to mutate, and that can lead to you having either cancer or radiation poisoning. There was a case about 15 years ago of a former Russian spy called Alexander Litvinenko, who was poisoned by alpha poisoning. They put it into his tea, he drank it, and it caused severe radiation poisoning, and he died very soon after. And he was irradiated, and people couldn't spend a lot of time near him because he was giving out such high amounts of radiation. So they couldn't go near him or touch him for fear of them becoming ill as well. Now you might be surprised to know that we use it in smoke detectors at home. You might be thinking, why have I got that at home? Surely that's dangerous. Well, it is if you were incredibly close to it or had your hand on your smoke or inside your smoke detector constantly. So you don't. They are generally more than 2 centimeters away from you. And it works in a fairly simple way. We've got our source and we have a circuit linked up and a detector. So we've got a battery in there as well and a buzzer. Apologies, it's upside down. As the alpha particles are passing through, they will ionize the air here, meaning that a current can flow. So we can get a current flowing through here. That stops the buzzer going off. If we get smoke coming in, so smoke comes in, there are no ions. That stops the circuit and the buzzer or alarm will sound. Obviously the circuit is a little bit more advanced than this, it's not just wires together, but it has a trip, so when the circuit stops, so when there's no current detected, the buzzer will sound instead. And that's how smoke detectors work. So all your smoke detectors at home will have a radioactive source inside them. Now it's not dangerous to you because those alpha particles can't travel any more than a couple of centimeters. So they're not going to cause any harm to you, so you don't need to worry about it. We're now going to have a look at beta particles. So beta particles are a high-speed electron. We write them as -1 there, so it's -1 protons. It's the opposite to a proton. It has no mass, and it is a beta particle. I'll put a little minus there because we can get positive ones, but you don't need to worry about that at the moment. They can be stopped by a thin sheet of lead. In air, they will travel about 2 meters. It says air there. They can be stopped by a thin sheet of lead or foil. Any kind of metal foil will stop them, very, very thin ones. Now, they can cause damage to your cells. So again, they can cause mutations in your cell, which can lead to cancer, but not as badly as alpha does. Its main use is to measure the thickness of foils or metals. So if you've got any tin foil at home, that's been rolled to the correct thickness using some beta radiation to measure it. And it works a bit like this. We have our beta emitter, and it will go through to the detector, which is linked up to a computer and feed back to the rollers. If too many particles get through, it means that the aluminium foil is too thin. So the detector detects that, detects too many of them, tells the computer, and the computer goes, you're rolling it too thin, make it a little bit thicker. So it does make it a bit thicker. If not enough of them go through, there's not many detected here, the computer says, there's not enough. It tells the rollers, you're making it too thick, you need to make it thinner. So we get a nice feedback system, and that controls the distance or the thickness of the foil. Obviously this detector will take into account any background radiation as well. So background radiation is that cosmic radiation we're getting just from coming down from space, so there will always be radiation around, but it will take that into account by working out how many beats it gets in a minute without the source and taking that away from whatever we get. A final one is gamma rays. So they are an electromagnetic wave. It's effectively just energy, a bit like light. It's the most penetrating, so it can go through everything, but least ionizing. So it will travel at the speed of light. And it needs to be stopped by thick concrete. Thick lead or concrete can stop it. It's necessary for me to get rid of these sources. We can't just stick them in the ground because it will constantly give out the gamma rays. We need to encase it in a very, very thick lead case or in concrete. It can pass through people without causing too much harm. It will cause harm, but not too much. One of the main uses are X-rays. We use X-rays. If you've ever had an X-ray, you've got some radiation going through you, and it goes straight through you. Having one X-ray, absolutely fine. 2 X-rays, fine. We get pictures like this. This is an X-ray of someone's chest, and we can see how much it has passed through. So these black bits here are where it's passed through completely to just the air, so we can see in the lungs here. These thicker bits here are the bones. So the bones, it hasn't passed through as easily, so it's left a bit of a trace on a film. And we can see the heart there as well, and we can see some of the bronchioles in the lungs, the spine and esophagus, liver down there, stomach and everything as well. But you might notice that if you've ever had an X-ray, the person doing the X-ray doesn't stay in the room with you. That's because they're not just having one X-ray, they are doing hundreds of X-rays a day. They will go behind a screen that's got thick lead behind it and pointing away from the gamma source so as not to expose themselves to too much radiation. Because even though it's the least ionizing, still too much of it can cause mutations to happen in your cells, in your DNA, which could lead to cancer. The final bit before we go on to the questions, staying safe around radiation. We want to make sure we're safe, and people who work with it or around it take precautions to make sure they're not at too much risk. That main risk being cancer. So they'll keep as far away from the source of radiation as possible. They won't go near it, they'll try and stay away from it as much as possible. And they'll spend as little time as possible with it. So if they're using it, they'll use it for as short a time as possible, and they will stay away. In hospitals, radiographers, people taking your X-rays, have a little badge that records the amount of radiation they are exposed to on a daily basis. And they'll wear that all the time. If it goes too high, they will have to take some time off work so they're not being exposed to too much radiation. Now, they don't handle the radioactive sources directly. They will wear gloves. They will use special tongs to pick it up with, so they're not having to touch it as well. Again, so it doesn't damage the cells, cause them to mutate and cause cancer. And they will keep any radioactive sources in a lead-lined box when not being used. You might be thinking, well, why are they doing this? So the lead-lined box will stop the alpha, beta and gamma coming out. Now, obviously, the alpha wouldn't be able to go more than a few centimetres. All you have to do is put it on a shelf more than 2 centimetres away from you, be fine. But it would irradiate the shelf, which could be a bit of an issue. The beta isn't going to go too far, a couple of metres, but we still don't want to irradiate anything around there, and the gamma could go for miles. By putting it in a lead-lined box, we stop it irradiating anything around us. And the lead is able to absorb quite a lot of radiation before it becomes badly irradiated. It's generally quite safe. There's also a whole ream of safety precautions that people have to follow when handling radioactive sources. We do have some at school. Hopefully we'll be able to show you at some point what they are and what they look like and how they act. We now have some questions for you to complete. Please pause the video and answer these 5 questions. When you're ready, you can press play. And you should now only be listening if you've answered all 5 questions. You can now check your answers. Pause the video to mark your answers. Thank you very much for watching. I hope this video has been useful. Don't forget to subscribe to the channel and have a great day. Take care. Bye bye.